Okay, in this example problem, I'm going to look at the graph shown here. It says the units on the horizontal axis of the figure below are in meters. So I'm going to go ahead and label that as an x-axis in meters. And I guess this should be v as a function of x instead of v as a function of t. Sorry for the typo there. And it asks how many wavelengths occur in 15 meters. And so I can see that in x in meters, this is what you would get if you used a camera to take a picture of this wave, where in your camera view you have distance in the horizontal direction. So it says how many wavelengths occur in 15 meters? Well, one wavelength is one complete cycle, and if you want I can draw a complete cycle here. I can label one complete cycle in green here. A complete cycle up and down and back to the start. 1, 2, 3, 4, 5. It looks like exactly 5 cycles, or 5 wavelengths, because this is the x-axis now and has units of meters. Exactly 5 of them fit in 15 meters. And so I can write that 5, if it'll let me write, 5 wavelengths in 15 meters. Okay? And now part B says find the wavelength of the signal. Well, if there are 5 wavelengths in 15 meters, then 5 times the wavelength is equal to 15 meters. And so the wavelength is 15 over 5, or 3 meters. Okay? And you can see that here on the graph, I think. One wave is something less than 5 here. One complete cycle is something less than 5 meters. Looks like 3 meters. Okay? And now it asks us to calculate the frequency of the signal given the speed. And now you can imagine this wave moving past us at a very high speed. And so the frequency tells us how many of these wavelengths pass by us in 1 second as it's moving past us. Okay, so imagine that situation there. As this thing moves past us, it's going to go bump, 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 and we want to know how many cycles pass in 1 second, and that's called the frequency of this signal. And the relevant equation here is that the speed, which is, this is a v for velocity, the speed is in units of meters per second, and the speed, I'm going to give the wavelength has units of meters, and the period has units of seconds. And so this is units of meters divided by units of seconds, and you can see that gives us meters per second on the left. In any case, 1 over the period t, lambda is the wavelength, t is the period, 1 over the period t is the frequency, and so I can bring the frequency up to the numerator like this. And now I need to solve for the frequency, and indeed I have the other two quantities. The frequency, if I solve for that, I divide both sides by lambda here, and I get the frequency as the velocity over the wavelength. And I can just plug in the numbers now. 200 times 10 to the 6th meters per second, and lambda is 3 meters. And this could be written as 2 times 10 to the 8th over 3. And this is nice because 2/3 we know is 0.667. It's really 0.666 repeated forever. I prefer to work with about 3 decimal places in these problems. 0.667 times 10 to the 8th. Or if you want to get it into a nice multiple of 10 here, why don't we multiply the mantissa by 100 and divide the exponent by 100, meaning we subtract 2 from it. And this gives us 66.7 times 10 to the 6th. Okay, so I've converted there, and then I can write this as 66.7 megahertz. Okay, and so the frequency, the units on frequency are hertz, and when I got a nice multiple of 3 here in my exponent, I could then use a metric prefix and get it into megahertz. So that's how you do this problem, and I hope that helps.